we saw it with some functions, like with polynomials. It's really easy to calculate the limit. The limit as x approaches c of f of x is just equal to f of c. You can just plug the c in. But that's not true for all functions. In particular, there are three ways that this could fail to be true. The first way it could fail to be true is this might fail to be true if the limit does not exist. So this might fail if the limit does not exist. So what might make it so the limit does not exist? Well, you might have it that your left-hand limit and your right-hand limit both exist, but they're going in different directions. That is, you may have your limit as x approaches c from the left may equal something other than what the limit as x approaches c from the right is. You might have a picture look something like this. Say your c value here is some value c. You come in from the left to one value, but coming from the right, you head towards another value. Therefore, your left and right limits would not be the same, so we'd say overall limit doesn't exist. So then certainly the statement can't be true because the left-hand side isn't even defined. Similarly, this could fail if the right-hand side is undefined. It would fail if f of c is undefined. For instance, you might have a function that at c has some vertical asymptote, perhaps. Then no matter what happens, maybe you're going up or you're going up. The limit there is defined. The limit at c is infinity from both directions, so the limit is defined. But at c, the function is not defined. Or you might have a function that doesn't have a vertical asymptote at c, but instead just has a hole at c. Just has a hole at c. Notice your left and right-hand limits are well defined. This has a limit. This limit is L. It has a nice limit. The limit exists, but f of c is undefined. The third possibility is that the left-hand side is defined and the right-hand side is defined, but they're not equal to each other. The equality might fail. So what would that look like? Well, it would be similar to this situation where you would have your left-hand limit and right-hand limit would both be going to some value L, but then your function f of c isn't equal to L. F of c is maybe it's defined down here to be 0. Then you would have your limit as x approaches c of f of x is defined. It's equal to this value L. But f at c is defined to be something else. Here it's defined to be 0. It's something other than L. So those are three ways it can fail. But notice all of these failings have to do with breaks in the graph. That is, in this graph, there was a jump here. In this graph, the lines didn't meet up. There was this asymptote, so there was a break in the graph, or a hole in the graph, or a hole that was displaced somewhere else. We call these breaks discontinuities. They're places where you have to pick up your pencil when you're drawing the graph. It's not a continuous movement. And therefore, if those are the discontinuities, we say the places where this holds true, that the limit as x approaches c of f of x is just f of c, we'll call those places where the graph is continuous. We'll say that f is continuous at c. None of these bad behaviors are taking place. There are no holes, there are no jumps, there are no asymptotes that you have to worry about. Now, notice these discontinuities come in two different kinds. For things like this break, it seems impossible to repair because you would have to move the whole graph up. Or here, there's a vertical asymptote, impossible to repair. Versus if you look at these other ones, if you could just move 1 point, if you could just fill in 1 point right here, you would make the graph continuous. Or if you could just move this 1 point up, You would be able to get rid of the discontinuity and make it continuous. We'll call this second kind, we'll call those removable discontinuities. These are removable because although there's a hole in the graph, you can easily fill it in by just moving a dot or adding a single point, a single dot. Whereas this other kind we'll call unremovable. It's more fundamental to the graph that there's a discontinuity there, and there's no way just by moving a point or two to fix that. In the next couple of videos, we'll explore some examples of continuous functions and see why they're so valuable. But for now, the big idea is just with continuous functions, you should think life is very easy. Whenever it's continuous, the limit will just come out to be whatever you get by plugging in the c. It's what you expect. There's nothing strange happening like a hole or a jump or an asymptote that you have to worry about.